Good morning. We have some event in the hall. Maybe I should close the door. All right, for the attendance question, we're using an area calculation. In 13.1, we mentioned that double integral can be applied or can be used to find area between curves. So in this question, we have two curves. Y equal x squared is a parabola. It looks like a graphic on the xy plane. The parabola seems to be the lower bound of the region. The line y equal to x plus 1 is the upper bound. So we have the upper bound and lower bound. Whenever we have the upper bound, lower bound, that could be the natural boundary for the y value. So trying to think about from the integration standpoint, think of the y value, all the y value, the point inside. The y value seems to be between these two boundaries. The upper boundary would be the y x plus 2, and the lower boundary would be y x squared. So y is 2, and that could be the natural boundary of the y value. On the other hand, for any region, you want to have the lower bound, upper bound, and left boundary, and right boundary. In this case, it looks like the upper bound, left, and lower boundary can be extracted, or it can be determined using the equation of the boundary. and then the left and right, you find it out. So for example, what exactly is this point as far as the x value, and what exactly is that boundary of this x value? So basically, we need to find intersection points. To find intersection point in math, you always set up an equation. So the upper bound is y equal to x squared. Lower bound is y equal to x plus 2. You can start solving the point of interaction by pairing the point of intersection. So y equal to x squared also equal to x plus 2. So then you can see that you gotta have x squared equal to x plus 2. And then setting it up will allow you to determine the integration bound. So then you have x squared minus x minus 2 equal to 0. Minus 2 equal to 0. We factor this into x minus 2 and x plus 1. So that way we determine these two x values at the intersection is x equal to -1 if x plus 1 equals 0, and x equal to 2 if x minus 2 equals 0. So these are the two intersection points. So we find out this is actually 2 for x value, and this is a -1. So then now we now have our integration boundary. It's -1 to 2 for the x. All right, and then for the y, we have the y boundary. The upper boundary is x equals 2. That was the boundary for the y value. So the lower boundary will be x squared. Okay, so pretty much we were using how the boundary is being determined to set up this equation. Looks like a double integral, but essentially, this boundary, you can see it's an integration of 1. So the antiderivative is y, and you plug in x plus 1 for y, and plug in x squared for y. So the inner integration, the integration value of this integration value is this part. Finish the integration. This part of the integrated value is x plus 1, is the upper boundary, minus x squared, that is the lower boundary.
Sorry, I
This
see.
is the inner integration. And we know we integrate the upper boundary, lower boundary, -1 This is the second integration. So finish this integration, that's the area between these two curves. It's one of those questions that we might have done in calculus 1. We're using integration to find area between curves. Now we're trying to reuse that idea. We actually put it into a double integration form. So the format change, maybe the fundamental came first. I hope that you're able to finish the integration to find out which one is the right area. I'll let you to finish the rest of the calculation. Suppose you can still finish the last integration. Integration -1 to 2, integrate x plus 1 minus x squared. Let me know what's your answer once you're done. I tried on the scanner already. Let's see. These are the one that has already submitted the answer online, and those are correct. Try to leave it on that page. Okay, that's right. Thank you. 6 answer that minute. 7, they're all correct. So I'm trying to finish the integration. Thank you. Any other questions? So it's the integration -1 to 2. The -1 and 2 is solved by using the solving the intersection point between the two curves. That is a little bit algebra. The rest of them is typical. The lower bound to the upper bound of the x value, and then there's the integration is the upper function minus the lower function of the integration region. So once we reach the last integration part, it's calculating. That's the calculation that you've done for integration, but we can't probably integrate it. Yes.
Sorry, I was just trying to write it down. I write down the
Okay,
process.
you're still over here.
Yeah.
So for 14 answer, all the answers that submitted so far, they're all correct. The process will be what's on the right is calculation of the intersection point. I calculated only the x value because the y value was the inner layer, so we have to use the actual function as boundary for y values. We didn't use numerical boundary for y. That's also because we choose dy dx. If you choose to do dy dx dy, it would be different. If you do a dx dy, then the inner layer would be the boundary for x. But boundary for x goes like this. It's this lower boundary, this upper boundary. And over here is this lower boundary, this upper boundary. It doesn't have a consistent line. So the lower boundary and upper boundary for the x value will be changed for a different y value. So dx dy is not a good choice. So because we have a natural boundary for y, we decided to do dy dx because it's more convenient. Not only can do both, one way or the other, but often one may be easier to calculate than the other one. So that's why we choose this method. So that you finish your calculation and else. When you finish,
Hold on.
x squared over 2 plus x minus x cubed over 3 in the integration next. Substitution. Fraction.
On here, so
Okay. So if we put in the 2, upper limit is 2 squared divided by 2, that's 2.
yeah,
2 plus 2 minus 2 cubed is 8, so it's 8 over 3. That is the upper limit evaluation. At the lower limit, you put in -1, but square of -1 still equals 1, so it's 1/2. And then -1. -1 cubed is still -1, so it's going to be +1 over 3. It's the last. So we would have visit. This is a 4. That
that'll be 3 over 2.
let me try to do calculation behind the 4 minus 8 over 3. Minus 1/2 minus 1 is -1/2, so it's plus 1/2. And then minus 1/3. 4 plus, what is it? Minus 8 minus 1 is actually minus 9 over 3.
You forgot the like the one, like the -1.
We did. This is 1/2 minus 1, which is -1/2. And there's another negative here, so that's.
Okay, never mind.
So if we combine this one with this one, we'll be getting this, which is actually -3. And then we combine the rest of them is 4.5, which will be 4.5. So finally, it will be 4.5 minus 3, and your final answer will be 1.5.
Okay, so what? So 1 over 3 over 2. So
X. Did I make a mistake?
nope. Don't think it did. I don't think so.
You guys have the right answers. Probably me that made a mistake. That's negative, right? Negative. That is -3.
It's 2x, ain't it?
Which one?
It's 2x because on top it's y equals x plus 2. Put plus 1 there.
Right, it's x plus 2.
Ah, that explains it.
So, yeah, right, that one was 2, so that one was 2x. So this is actually 4. So this was 6. So this was 6.5. Still do. Six minus 8/3. And minus, there's a 2 here as well. There's a 2 over here. So this is a plus 3 over 1. And that was making it 6 plus 1.5 is 7.5. This one should be 7.5. 7.5. Anyway, obviously you guys are better at me, and especially I decided not to use a calculator. My calculation error is starting from here. So okay, but that's it. I don't know the right answer by me making the mistakes. Okay, let's see if I still.
I did it. Oh, that did.
I don't know.
It probably just didn't pick up, so.
So I think I have funny answer now. Anyone else? I think that should be everybody. Okay. So the final answer is B, as you already see from me making a couple of mistakes in there. That's the upper bound. It should be x plus 2. I copied over x plus 1 for some reason. Right. So let's do a practice question using double integral area calculation. Do you have any question from the homework that you want to ask? Any question over the homework? So I assume we're doing okay with the homework. We are already started with chapter 13. Let's see. So I did post the homework 13.1 and 13.2. Maybe I should reopen 13. They're still open. All right, so today let's try to finish 13.2 and possibly moving on to 13.3. And it's basically we're looking at integration with multivariate function. All right, so 13.1, we were looking at iterated integral and also looking at how to calculate area using double integration. Now, this section, 13.2, we were doing. Get it to run. Right, we're doing volume calculation with double integration. What we were already talking about. So with integration, we're able to calculate area already, but now we're looking at volume calculation using integration. So as you can see, this is the numerical method for calculating integration. The limit of the when the precision gets more important, the limit of the definite integral calculation, limit of Riemann sum will be the definite integral. Try to review volume calculation under a surface. The surface is z equal to f of x, y. It's a two-variable function. So the area below the surface, assuming that the integration region is the domain of the function is on the xy plane. You see that little circle that we see. So calculation of it, you can think of it. You can look at a detail of the volume and expand it from there. So look at a small piece of that volume, which is the red bar. The height of this bar is the function value f x y. So the value. The base area is a little square or a little rectangle, which the area is calculated by length times waist or delta x times delta y. So f of x times dx dy is a small volume calculation, but there's many, there's many small volume actually we're supposed to add it all together. As quotation gets more and more dense, we can have the volume calculation, that summation will be more accurate. So limit of that would be our volume calculation. We can use double integral to calculate the volume under a certain, under the surface of the equal to fxy. Right, we went over a couple examples already. The integration region is very so we have to look at each individual integration region to determine what will be the best way to calculate it. Now, you would choose dy dx if the x has a numerical boundary, the y value or the upper bound and lower bound integration can be easily identified as two function. On the other hand, we would choose to use dx dy if the x value is within a variable boundary, but the y value. So it really depends on the shape of the integration region. And we went over a couple of examples. The first example, which has a region as a rectangular region, is that little rectangle with a corner point 3, 1, and 4, 2. So you are integrating a function, then the integration limit will only be affected by, will only be determined by the integration region, which will be that little rectangle. So in this case, the lower boundary and upper boundary for the x value is 3 to 4. Lower boundary and upper boundary for the y value is 1 to 2. So that already. So if it's a rectangle integration region, the integration limit shouldn't be too hard. And except we try not to switch x and y, actually on the right boundary for the inner layer and the outer layer. So then the calculation follow the calculation rule. We've done that last time. So you would make sure that you integrate the inner layer first and then move on to outer layer integration. That's why it's called an iterated integration. And then the final answer, of course, is so that's what's being presented in the textbook. I'm trying to go through each step so we can see what should be determined first and what should be determined next. And of course, you can do it both ways, dy dx or dx dy. All right, this one, the integration function is the surface that we see in the picture. The integration region is a triangle. So we're using x-axis and y-axis and line as the boundary of the triangle. So again, this is the kind of situation you can do dy dx or dx dy. Either way is fine. Now, if you want to do dy dx, then your x boundary has to be identified as two number for the x value. And then the y value have to have function boundary, upper boundary and lower boundary are a function that y equal to. Make sure you have your y solved in your equation. So for example, the upper boundary should be y equal to 1 minus x over 2. So after we determine those rest of the integration, it takes some practice with accuracy, but we try it with practice to get better at it. And the second one is to integrate the same function with dx dy. Both of these methods will present the same final answer, but the process is slightly different. For example, the integration limit will be different. If you are doing dx dy, then the y is on the outer layer. So the boundary for y value is 0 to 1, but then the boundary for the x value would be 0 to that line. The line is x over 2 plus y equals 1. You have to solve the x from it. So we move the y over and then time 2. That's why the upper boundary is 2 minus 2x. And okay. So then according to all these examples that we went through, we have a summary saying your integration limit will only be determined by the integration region. It has nothing to do with the function that you're integrating. So f of x will stay as f of x, but r is the one that will dictate how you identify your integration limit. These are the property for integration. It's the same integration property that you would learn in calculus 1. This is already been mentioned before. And then we went through this one. That's this one has a symmetrical integration region. It's a -1 to +1 on the x value. So when you integrate sine x on the symmetrical integration region, sine x is all functions, integration equal to 0. And moving on, this is the one that we haven't talked about, so I'm gonna start from here. This question says we want to integrate 4 minus y on this integration region. The integration region is bounded by y squared equal to 4x and x squared equal to 4y. So if the x squared equal to 4y means y equal to x squared, it's a parabola. On the other hand, the y squared equal to 4x is a symmetry version. So we would say that these two curves of the boundary, they're symmetrical about the line, like they're like inverses of each other. So what do? We can graph them. So if you graph y squared equal to 4x, it's a red curve that we have. It's the upper boundary. Now the x squared equal to 4y is a lower boundary. So our integration region is a region within these two boundaries. Okay, so we were supposed to integrate this function. We integrate 4 minus y on this integration region. So then the number one thing we have to do is that now that we're doing which integration limit is appropriate. In the textbook, we choose to do dx dy. So then the y has to have a numerical boundary. So we have to find the lower value for y and the upper value for y. On the other hand, the x value can have the lower boundary for the left boundary and the right boundary for the x. So in order to do either one of those, the number one thing is we got to find the point of the intersection. So we're going to pair these two curves. In order to determine the integration limit, we have to find the point of intersection. This one is not given. Yeah, so it's not a rectangular integration region. So we pair these two equations. Y squared equal to 4x, x squared equal to 4y. So now it's time for solving of the intersection point. How do we solve it? Right, this is a solving process. This is an awkward way of me doing it. You can do it either way. So I decided to take one equation. These two are pretty much symmetrical. You can take the second equation or you can take the first equation. But in this first equation, I solve for the x value. So divide both sides by 4, x equal to 1/4 of y squared, and then plugging that to the second equation. That's what happened. If you square the x, it will become 1/16 and y to the 4th power. That equals 5. Now you have the equation of y, and all you have to solve for the y value. Then we have the y. I mean, y is supposed to be dy, right? Dx dy. Y has to have numerical boundary. So what I went ahead to try to solve it. Multiply both sides of the equation by 16. Y to the 4th equal to 64y. And then you can see if y equal to 0, you can't divide both sides equation by y. So I want to divide both sides by y's. So then one of the equation that we have to rule out is y equal to 0. So y equal to 0 is one solution. If y equal to 0, y to the 4th equal to 64y. Now the other case will be if y is not equal to 0. If y is not equal to 0, you divide both sides equation by y. You have y cubed equal to 64. And then cube root of both sides equation will have y equal to 4. So y has a numerical boundary 0 to 4. That made it possible for us to look at our integration limit. So the number one limit we need to determine is the dy. So we have to have the lower boundary, upper boundary for the y value, which should be a number that we just find out. 0 to 4 is the boundary for y. And next is we need to find the boundary for the x value. We need to solve from these two curves. We need to solve the x value from them. So start with the upper boundary. The upper boundary is y squared equal to 4x. You solve the x value from it, divide both sides by 4. So the lower boundary for the x value, which is really the left boundary of the x value. The dx, you got to solve for the x equal to 1/4 y squared. Now the upper boundary for the x value is you start with x squared equal to 4y. And then we have to solve for the x value. We have to take square root of both sides equation. There we have our x value. That will be the upper boundary. So after determining the lower boundary and the upper boundary, now it's calculation time. Right, so when I started calculating, when I started having this habit of not writing the outer layer of the integration, I just zoom in on the inner layer of integration. We have to integrate from 1/4 of y squared to root of 4y. That actually is 2 square root of y. You can take the 4 out of the roots. Integrate 4 minus y dx. Now, dx means 4 minus y really is a number in relation to dx. So the antiderivative is 1 dx, antiderivative is x. Right, so that's the antiderivative. We have to plug in upper limit and lower limit. Remember the upper limit and lower limit is supposed to be the x value. So only the x value are substituted. So that would be upper limit minus the lower limit. So that's what we have. So this is everything that you need to calculate as far as the interlayer of the integration. Now we're done. The integration on the inside is done. Move on to integrating the outer integration. I try to write as less because in the past I write everything. It's a really long integration. So I decided not to write the outer layer of the integration as I was calculating the inner layer. So that's the last layer of integration. Realize that now there's no more x because the dx is done. So now it's all dy, it's integration of y variable. So the rest is the same as what you see in the textbook. So I decided not to copy them over. All right, so you can see what we have is over here. All right, so what we have is the same here. It's a multiplication of two term times two term is 4 term. We have to write it term by term expanded. Then we apply power. So negative y squared times over 4 times 4 is negative y squared. Negative y squared times negative y is positive y cubed over 4. So that's the multiplication of these terms. The first one has a root of y. Root y is y to the 1/2 power. So y to the 1/2 power times 4. So that's 8 times y to the 1/2 power. That's this term. And then this one, if you multiply the 4 root, this one, right? The 2 root y times y, the y will be 3/2 power. And then the 2 times the negative y will be negative 2. So that's the power form of all the function of y. And then you apply power rule for each term. Okay, and apply power rule with the antiderivative and plug in 4, which will be the final answer. So these are all to finish the calculation of this question. Any question? Okay, I hope try to explain the determination of the integration limit a little bit better. In the text, this is all we have. In the textbook, this is all we have. So I try to explain how do we determine the integration limit. Normally, it's not that detailed in the textbook, right? So that's this example. Next example is rewriting this iterated integral and comment on the feasibility of the evaluation. So why do we have to do this? Because you see here, the inner layer is integration e to the negative x squared dx. That does not have antiderivative. So we don't have a formula to calculate this integration. We cannot integrate this way. That's the situation that we are facing sometimes. If you do dxy, we cannot do it. But if you switch the integration order to do dy dx, we actually can do it. So this made it more the reason for us to learn how to switch the integration order. So here we are. Number one thing is if we want to change the integration order, we have to identify exactly which region are we integrating. And so some of you are better than I did. Me, I have to visually see the integration region in order to switch the order. So I'm trying to identify, according to the integration itself, the outer layer is dy. So y is naturally between 0 and 3. The inner layer is dx. So x has an upper boundary, x has an upper boundary, lower boundary, x is between y and 3. So the integration notation itself already indicated the integration that we're doing. So y is between d and 3, and then x is between y and 3. X equal to 3 is a vertical line. X equal to y is this line. It's y equal to x line. So after drawing these boundary, upper boundary, lower boundary, left boundary, right boundary, we have this triangle. All right, so now if the integration region on the xy plane is clear, now we can try to look at how we look at the integration region. Now, according to the integration order, if you're doing dy dx, then x is on the outside of the integration. So x has to have numerical boundary, and that is easy. You look at the triangle, x is between 0 and 3. So 0, 3 for the dx, x boundary. Inner layer have to find the boundary for the y value. Now, if you look at this triangle, every part of it will have a lower boundary of y at 0, and the upper boundary of y is on the line. So on that line is y equal to x, but you want to represent the y with a formula for y, which is x. So the upper limit is x. You look at it, so you can see the integration limit are being changed, and if you double check those boundary, it's indicating the same integration rate. So that's after we change the order of operation, and then we can look at calculation. So here, when you are calculating it, we will always, it's iterated integral. You always have to finish what's on the inside layer of the integration. So we have to do dx dy first. When we do in dy, e to the negative x squared is independent from the y variable. So these are like numbers in relation to the y variable. So that's number that you copy down, and then that was 1 dy. 1 dy, the antiderivative is y. Now we put in integration limit, which will be x minus 0, x, y equal to x, and y equal to 0, and we subtract. So it's going to be x, and that's what we have. Sure, we've done. So substituting the x for y, we have x times e to the negative x squared. So that's what we have in the inside of the integration. Now we're going to move on to the outside integration. So if the inside integration is done, we integrate 0 to 3 dx. That's the last integration we have to do. We kind of have to do a substitution method. But instead of doing substitution, I was looking at e to the negative x squared. It has a derivative that equal to negative 2x. So I decided let's write negative 2x. That way, negative 2x e to the negative x squared, put interchangeable. This is the derivative of e to the negative x squared. So if I create a negative 2x, because that's the derivative of negative x squared. So I have to multiply negative 1/2. I mean, there are already x there. If you add a negative 2, you have to add a negative 1/2. Not add, we're multiplying. All right, so negative 1/2 is a coefficient. We can backtrack and see this function has this derivative and therefore equal to this. So when you go back and look at the entire equation, the equality is true for every step. So once you find the antiderivative, you plug in 3 and 0. Right, that's the final value of the integration. Any question? I multiply the negatives just so it's easy to say it's according to change. That's already a question. All right, if you feel like this is awkward to understand, you can also do a substitution method. You can make u equal to negative x squared, then du will equal to negative 2x dx. So then you can change the variable, right? So then the negative 2x dx is the du. This will be e to the u du. The antiderivative will be e to the u. And of course, you have to have the negative 1/2 as coefficient because of the change of variable question. So this is the final answer. And then you can also see the reason that we have to change the order of operation. We can't do it without changing it. That's the answer in the text that we evaluate. The decimal answer is roughly 0.5. Okay, there's something else that the session was added. So it's the definition of the average value function. We had the average value of a function in calculus 1 back then. If you had a single variable, the average value of the function is being determined as, just try to compare with calculus 1. Right, so if you got a function that's being defined as a y equal to f of x is defined or continues on the interval a to b. This is for one variable function. So what is the average value of a function? F average is being defined as integration of from a to b integrated function f x x. And then we divide it by b minus a. So why do we define it that way? Because if you look at the integration, this way, right, this is the a to b. Some of your function are higher, some function is lower, but we have to use the total area to divide by this side. We'll be calculating like even out like this height be the average height of the function value. Okay, so basically the method allows you to roughly estimate what is the average y value. So that's the idea. For example, if this is a constant, the area will be rectangle. The rectangle divided by this is kind of like length. Area divided by the length will be the width or the height of the rectangle. So that the calculation does have this geometric meaning on the way determining average value. Here we do something similar. So you have this is the x-axis and y-axis. Right, so this is our z-axis. So say you got a surface over here, and this is the base region over here, the base area. This is a double integral of the integration region. This provides the area at the base. Now this is a height, like the height. So the total area below the surface is three-dimensional. So you take this three-dimensional volume divided by the base area, which is calculating exactly what the average height here. So in this calculation, the numerator calculated the volume under the surface. The denominator calculated the area of of this three-dimensional volume. The base area is calculated. So volume divided by the base area ends up giving us the average height, so average function height. That was the calculation. So following that, we give an example. This is the one that we have talked about before. If we integrate 4 minus y over the region bounded by y squared minus 4x and x squared minus 4, so then this integration will give us the volume below the surface, which we have already finished. Okay, so we finished this calculation. We got the 176 over 15. Now, if we don't have the f, we have a 1. That will be area calculation between these two curves. Those area calculation end up being 16 over 3. So if you take this one divided by this one, you get roughly 2.2. So on average, the function value is 2.2. So we can actually think about this. The y value, if y equal to 0, 4 minus 0 is 4. So that's the height of the z value. Now, on the other hand, if the y equal to 4 and 4 minus 4 is actually 4. So the y value is actually somewhere between 0 and 4. And then here we're going to calculate the volume divided by the base area and get average height of 2.2. It seems to make sense. I mean, the y value seems to be somewhere in there. So on average, 2.2. Any question? So this is a definition. You're writing the volume calculation as a numerator part of it, but the actual average value of the multivariable function seems to make sense. Right, so this is the majority of the 13.2, which focused on volume calculation below a function. And let me try to start a little 3.3. And now 3.3, the title is called Double Integration with Polar Coordinate. How many of you have heard of polar coordinate before? Okay, so basically polar coordinate is not brand new because I think we mentioned before, when you make x equal to r cosine theta, y equal to r sine theta, we're switching our variable from x and y to r and theta. So using r and theta as a coordinate system is the so-called polar coordinate. Now, why do we want to use polar coordinate? Because sometimes the integration region, as you can see, integration region can be hard to do if the edge is in a weird shape. So here we want to provide some convenience when the integration region is circular shape, circular related shape, then polar coordinate is better. Better yet, sometimes we may have elliptical coordinate in a sense. So kind of like a polar coordinate system. So let's talk about how do we use polar coordinate? How do we change the double integration to a polar coordinate integration? So you may start out have x and y in your integration, but then in the end you want to switch it to polar coordinate and in order to make the integration easier calculation. So let's look at some calculation related to polar coordinate. This is to try to review the formula for a circular some circular calculation. If you got a circle, then part of the circle is called a arc. Okay, so I color that part related to angle theta. We have part of the circle is called a arc. The length of the arc is r times theta. Okay, basically the theta is a reading measure. According to the reading measure, the angle is a ratio between the arc and the radius. So that's why this equation will actually make sense, because by definition, theta equal to the arc, which normally use s divided by r. That's how theta is being defined, which is why s will equal to r times theta. Okay, so we do require the theta has to be a reading measure for the equation that arc equal to r times theta. So the equation is only true when theta is in reading measure. Okay, the other formula is area. So here the area over this part. So I'm trying to represent the length on the side, the length of that part. The arc is a small part of the whole circle. It's a line, a really small line, a really small piece of the curve at the edge of the circle. Now, a sector is a part of the whole, including the inside. Area of the sector is like a small piece of the pizza. So this area calculation, the calculation formula is 1/2 r squared times theta. How do we remember it? The way I remember it is 1/2 base and height. If you look at that sector, it's kind of like a triangle. So the base is the arc. The base is r times theta. The height of the rectangle is r, so it's 1/2 times the height, which is r, times the base, which is r theta. So that's 1/2 r times r theta, which is 1/2 r squared theta. So that's how I remember, because area equal to 1/2 base times height is really a persistent formula that seems to be everywhere, area of a triangle. So anyway, keep in mind that's our formula. Now we're trying to divide a way to represent how to calculate a small piece of the area if the coordinate system is in polar coordinate. So here we have a area. Suppose this is a polar coordinate represented region. So if you look at that small part of it, and then you can see the r, the radius, is being sliced into small radius, bigger radius, bigger radius. So according to different radius, there's different value, and then the angle are also changed here. So in order to represent that part of the area, what do? We can do, so this is the calculation. So the change of the area, this part is calculated by a sector, the bigger section. Maybe I can use a cursor, so everyone can mean. Take a picture. Pointer. Okay, so what's this part? You can think of it as this bigger sector minus the smaller part of the sector. This bigger sector, take this part, has the radius r2, and then the angle is called a delta theta, because this is the angle, smaller angle. This is a bigger angle. So the bigger angle minus smaller angle is a delta theta. So the angle is delta theta. And the radius here is r2, radius here is r1. So the bigger sector will be 1/2 r2 squared minus the delta theta, which is the angle. Then the smaller sector is 1/2 r1, this is r1 squared times the delta theta. So subtraction of these two is dA or delta A. It's a small area calculation. So we factor the common factor, which is the angle. Then we have the r2 squared minus r1 squared, and a square subtracted follow the formula a squared minus b squared equal to a plus b times a minus b. So here is a plus b, here is a minus b, or r2 plus r1, r2 minus r1 multiply equal to r2 squared minus r1 squared. So there we have it. So why do we do this? Because when you have r2 minus r1, like bigger radius minus smaller radius, that's dr or delta r, dr. So this is dr, this is d theta, delta theta is the d theta. Now r2 plus r1, when the change in the r is really small, you can assume R1 equal to R2. So R2 plus R1 divided by 2 is really R. So this is R dr d theta. So what we're trying to say is that dA equal to R dr d theta. We're trying to use a geometric look at it to devise a change of variable routine. So down here, typically in the rectangular coordinate system, dA is equal to dx dy. So dA is dx dy or dy dx are changeable because they are rectangles, independent, it's perpendicular. X coordinate and y coordinate are perpendicular to each other, so the multiplication, the order can be switched every calculate. dA can be calculated with dx dy or dy dx. But on the other hand, if you want to use polar coordinate, dA actually equal to R dr d theta. So it's interesting that we have this extra R in the computation there. Okay, so this is pretty much a geometric way through those studying the picture. We realize dA equal to R dr d theta. However, there's also an algebraic way of thinking this, at least our textbook's way. Okay. There's another way to connect them or remember the reasoning in here. That is, we have x equal to r cosine theta when we convert the variable from variable xy we convert it to variable r and theta. Y equal to r times sine theta. When you try to find the derivative of x with respect to r or respect to theta, derivative of x with respect to r would be cosine theta. Derivative of x with respect to theta is negative r sine theta. And find the derivative here, because it's really a differential, like dA, right? You're gonna find the dx, you're gonna find the dy. So here I'm trying to determine the dx dy. Now, if you try to find derivative of the y variable with respect to r, you get sine theta. With respect to the theta, you will have r cosine theta. So here is going to be the matrix of their derivative vector. So this is the change of variable. If you want to find dA, you're going to find dx dy, and here we have our dx and dy. So the determinant of this would equal to, you will do cross multiply, there you have r, see, dx, this is supposed to be dr, and then here's dr, and this is d theta, the partial derivative with respect to theta times d theta. This is the total differential for x, and here is our total differential for y. This is the dr, and this is the d theta. So we cross multiply. You have r cosine square theta, all right, minus negative or plus r times sine square theta. Okay, and then this is a dr d theta. This is cross multiply, also dr d theta. So we have dr d theta. So the determinant of this matrix is equal to r factor out, and then cosine square plus sine square theta equal 1. So it's r dr d theta. So this is more of a differential way of determining the differential of our variable, because ultimately our representation of dy is dx d theta. So if you find the total differential for dr and total differential for dy, and there you have it. So this is another way to devise or try to understand the change of variable causes our differential of the area to be different. Anyway, I hope that kind of makes sense in a way that we kind of see why do we have base to R. Another way to understand it, one way or the other, we try to make it easy to remember. Before, dA equal to dx dy, and dx and dy both represent lengths. Dx is changing the x variable, it's a small change in the distance. Dy also is a length. However, if you switch it to dr d theta, BR is still change of distance. Its radius is a distance. However, d theta is not. So we're missing, if you only have BR d theta, we're missing a distance information in there. And theta itself is only a ratio of distance. So theta does not have unit, does not represent distance, which made more sense that we have to multiply another distance information to make sure the dA is a two-dimensional measure. Anyway, one way or the other, there's a lot of reason that we have to multiply this actual R when we change the variable. So here is the how we convert from a dx dy, how we convert from xy variable to the R and theta variable. We do have to do a change of variable whenever you have x in your integration function. X has to be switched or replaced by R cosine theta. Y has to be represented with R sine theta. And the variable has to change to the dA has to become R dr. So there's actual R in the integration. Also, the integration limit has to change to the polar coordinate. And that, of course, will be different in the integration limit for x and y. So let's look at some example on switching the integration order, switching the integration variable. So here we have, let's say we try to find the sine volume, the volume under 4 minus x minus y over the circular region x squared plus y squared equal to 1. Okay, in this question, the x squared plus y squared equal to 1, it basically is the R equal to 1 circle. So x squared plus y squared equal to 1, x is R cosine theta, you square, and then the y is R sine theta, and then you square. So then obviously we get R square cosine squared theta plus R square sine squared theta equal to 1. So then R square equal to 1 because cosine theta, R square is a common factor, cosine squared theta plus sine squared theta equal to 1. So then R is positive, R is really R equal to 1 is the outer boundary of the region. So then in the integration for dr, R goes from 0 to 1, and then theta is a whole circle. So theta goes from 0 to 2 pi. That's going to be the boundary for the integration region. So here we are. As we try to switch the variable, the integration function change. It was originally 4 minus x minus 2y. Now our integration function is 4 minus R cosine theta minus 2R sine theta. So that's the x, that is the y. R sine theta is y, R cosine theta. So our integration function changed. On the other hand, the dA is now being represented as R dr d. There's actual R that we have to integrate. And then the R, the integration limit for R is 0 to 1 because it's a unit circle. Unit circle, the maximum value for R is 1, the minimum value at the origin R equals 0. Theta, if it's a full circle, 1 revolution is 0 to 2 pi. Right, so from there inside we have to do dr, and you can see this is the R part. So integration for R, we will have 2R squared. Integration R squared, we have R cubed over 3. All the other one are coefficient we have to follow. So that finished the interlayer of the integration. So this integration, integrate the R accordingly, and then plug in R equal to 1, R equal to 0. So when R equal to 1, these are 1, that's 1, that's what we have. Now we have to integrate with respect to theta. 2d theta, we have 2 theta. Then cosine theta integrated is sine theta. Sine theta integration, negative sine integration is cosine theta. Then we plug in 0 and 2 pi. And then you can see with sine theta, sine 2 pi equal to 0, sine 0 also 0, cosine 2 pi cosine 0 also both equal to 1. So this part of the integration equals 0. The 2 theta is 2 times 2 pi is 4 pi. So the final answer is 4 pi. Any questions? Okay, so it's exercise on switching the integration variable. This one, if you are using rectangular coordinate, you will have variable boundary on either x or y. So with polar coordinate, the R and theta has R's from 0 to 1, theta from 0 to 2 pi. So it's a lot more convenient with polar coordinate. So this is the kind of question that's hard to do with rectangular. All right, moving on to the second example, we want to find the volume under the paraboloid over the region bounded by the circle x minus 1 squared plus y squared equals 1. And the picture of the circle is the inner circle there. This is a circle center at 1, 0, radius equal to 1. So if you write into a polar coordinate, that's actually r equal to 2 times the diameter, 2 times cosine theta. This is on the positive half of the x coordinate. The circle on the outside circle has a diameter 4. So if you write it into a polar coordinate, the equation will be r equal to 4 times cosine theta. It's all on the positive side, so it's cosine theta representation for both. So anyway, I'm trying to think about how we represent both of these two curves. Right, so here we're gonna try to follow step by step how do we calculate this. We were integrating 4 minus x minus 2 squared minus y squared according to our idea of changing variable, x being represented by r cosine theta, y also is substituted with r sine theta. So it looks like this. And on top of that, that's our function, right? And then instead of dA, now we have r dr dθ. So this actual r has to be multiplied. And there are a lot of things that could be simplified. You see the original function, it's like a pretty lengthy process. There are certain parts that could be simplified. You see the x minus 2 squared has a 2 squared, that's 4. This is a 4 minus, so probably 4 minus 4, we can cancel some of the common terms. So down here, I'm trying to expand it. R cosine theta minus 2, you square that, you have r squared times cosine square theta minus 4r cosine theta and then plus 4. So then 4 minus 4 cancel that. And then r squared cosine square theta and there's r squared sine square theta. These combined is minus r squared. So then we end up having two terms. Two of these combined, 2 of these cancel. So out of the 5 terms, only 2 terms left. Any question? So this is our integration, but on top of that, we have to multiply the r dr d theta. And here we are. So our integration function multiplied by r dr d theta. So this is what we have to integrate. But before, this is just changing the integration function. After changing the integration function, now we have to determine the integration limit. So how do we determine the integration limit? I was talking about this representation. The polar representation of this one is r equal to 2 times cosine theta. Polar representation of that one is r equal to cosine theta. If you wonder how we come up with that, you can do it. You can do r cosine theta minus 1 squared plus r sine theta squared. And those square are going to have some of the term cancel each other out. Like the 1 will cancel this one, and then the r squared cancel the r squared. And eventually, you're going to simplify into this. Same thing here. You can do a substitution of the variable x equal to r cosine theta, y equal to r sine theta. Eventually, many terms cancel. Like the 4 on this side will cancel the 4 on the other side. So if you're seeing canceled, you will probably get that one. Right. So these two are some of the circle. Whenever we have a circle in polar coordinate, they tend to be a lot shorter. So these are going to be the lower boundary. Lower boundary is the inner circle. Upper boundary is the outer circle for the r. That we can start writing the lower boundary, upper boundary for the r, and this for theta is 0 to pi. Because each one of these circles, you don't have to go 0 to 2 pi because 0 to pi already covered the whole circle. For example, the small circle here, see this is 0, 0 and 45, and then 90 degree is already covered this half circle. So then the other like 100 degree like this, and 120, and so then after you reach 180, it's already the whole circle. So try to trace the circle, trace the polar coordinate circle to know what is the appropriate angle that you use for theta. So in this upper boundary, the theta, the upper boundary is not 2 pi, it's actually pi. If you have a circle that's on the side of the origin. If you have an origin inside the circle, you probably have to go 0 to 2 pi. Whenever the origin is on a point on the circle, you normally don't need 0 to 2 pi. 0 to 1 pi will be enough. So anyway, we integrate the inside remember the r have to be multiplied to it. So r squared times r is r cubed. R cubed integrated r force to 4. This is the r times r, so it's r squared. 4r squared integrated is 4r cubed over 3. The cosine theta just follow, and we plug it up in the middle of it. And you can see it's a cosine theta cubed times cosine theta to the fourth power. All of these are cosine theta to the fourth power. Combine the coefficient, we have this. This is integration on the inside. And with that, we realize we have to integrate this from 0 to pi. Integration of cosine to the fourth power of theta, it takes on, we don't have formula. So in the book, we spend a few more paragraphs on expanding the cosine to the fourth power. So here we are. This is how it's being expanded in the text. So eventually we have to integrate from 0 to pi 44 over 3 cosine 4 theta. Cosine theta to the fourth power. So here we are. Cosine theta to the fourth power is cosine squared power times cosine squared power. Now, cosine squared power can be represented using the power reduction formula. So cosine squared theta is 1/2 1 plus cosine doubles angle. So these two multiplied, and then we expand 1/2 times 1/2 is 1/4. This is a square. Using the square formula, we expanded. And then that's degree 0, that's degree 1, that's degree 2. The degree 2 has to be reduced power again. So apply power reduction formula is 1/2 1 plus cosine double angle, 2 theta double as 4 theta. Now we have this, and then we combine the like term again. And finally, we have the representation of cosine 4 theta. Cosine 4 theta, the problem is the power is too high. So we applied power reduction formula twice until we have the degree 1 formula. These can be easily integrated. So we decided to go from there. This is a cosine 4 theta, power 4 theta, expand it to this, and then we multiply the coefficient or not. We integrate each one. 0 over a integrated into 0 over a theta, cosine theta integrated sine 2 theta, now on 2. So cosine theta can be integrated using the integration formula, and we plug in pi and 0. As an outcome, sine 4 pi sine 2 pi, they all equal 0, so these are all 0. Only the 3 over a theta with theta replaced by pi, that's the calculation. So it's 44 over 8 simplified into 11 over 4 pi. So that will be the final answer. So this one takes some time because the trigonometry part is time consuming. Maybe some of you are also having difficulty identifying the polar equation of the curve. If that's also something that we're not familiar with, maybe we need to go try to write out the x equal r sine r theta, y equal r times sine theta. Now we can expand those two equations into these two. So it's converting from rectangular equation to polar equation is the full solution of this one. All right, let's try it again. And this is try to find the volume under this curve of the sector of the circle with radius A. Now, one of the problems with this question is radius is A. So it's not given. That means your actual calculation of volume will also end up being using the A as part of the answer. So, but at least you won't have difficulty identifying the right limit. So if it's a circular integration region, the theta is from 0 to 90 degrees or 0 to power 2. The R is from 0 to A. So here we are. So after changing, this is going to be 1 plus r, x squared plus y squared equal to r squared. 1 over r squared plus 1. And then we have rd theta. So that's the integration function. Now the integration limit will be r from 0 to a, theta is from 0 to 2 pi over 2, 0 to pi over 2, because we only were looking at the first quadrant, in fact, the first quadrant on x1 point. So 0 to 90 degrees. With that, this can be integrated into 1/2 natural log of r squared plus 1. That is, you can do a substitution method to say it. If r squared plus 1 equal to u, then du equal to 2r dr. So then r dr is part of du. There's 1/2 to balance the coefficient. So this this is gonna be, du over u, or one over u. Integration of one over u is logarithm u. U equal r squared plus one, so that's the antiderivative of it. Or you can look at this calculation, the derivative of the natural log r squared plus one is the 2r over r squared plus one. So differentiation of natural log. So plug in a and 0, we'll have, this is an antiderivative. Now this value, 1/2 natural log a squared plus one, is independent from theta. So bring that out of the integration. The d theta into 0 to pi over 2 will just give you pi over 2. So it's pi over 2 times 1/2 natural log a squared plus 1. That's the answer to the question. So this question does not have a lot of difficulty because the integration region is a quarter of a circle. So often the integration region causes some whatever difficult that you have identifying the integration limit is caused by the integration regions. Let's see. All right. This is one of the textbook example explaining the volume of a sphere. I wonder if you already know the volume of a sphere. Anybody already know the formula for what's the volume of a sphere? A volume of a ball. Do you know? It's one of the geometry formula. No? Okay. So here we are. Because it's related to circle, you probably have to have pi in the final answer, but the rest of them, let's see. So here are the calculation. Maybe we can do it ourselves. So we will also use a so I feel like if we follow the PowerPoint and race through the PowerPoint all the time, we won't see any difficulty. So you got a sphere. Let's see how we draw a sphere. Okay. So how do we represent a sphere? That's the same. Find the volume of sphere. What's a sphere? Sphere, let's draw a xy axis, x-axis, y-axis, and the axis. I think we had the surface formula for sphere, which goes x squared plus y squared plus z squared, which equal to radius is a squared. So that's the surface, like the equation represents a sphere. But we certainly want to have a like the surface represented in the z variable. So you solve for the z from the z equal to you move the x squared y squared over, so it's going to be a squared minus x squared minus y squared, and take square roots, which is the upper half. So if we find the volume within the upper half, and then times 2, because the upper half have a positive z, the lower half has negative z, so we're probably easier to present a positive z. The negative z we can just double. So the whole volume calculation will be volume under the upper half of the sphere, which is integration of a circular region. The integration region are going to be this circle, which is radius a, so it's on the xy plane. So the integration region is at within the circle of x squared plus y squared less or equal to a squared. That's a circle with a radius a there. So that's our integration region. So on that integration region, when I integrate this, this is an a squared minus, this is our surface formula. That's our surface formula, which has a positive z, minus y squared. Right, and then remember we want to do polar coordinate, so we would do r d r d theta, r b r e theta. Okay, when we do that, we will need to know the integration limit for theta. In this case, the origin's inside the circle, so we should have 0 to 2 pi for this theta. And then for the r, which is the radius should be from 0 to a, because we have a circle of radius a here. And then the x equal to r cosine theta, y equal to r sine theta. So x squared plus y squared equals r squared. So in this integration function is root of a squared minus r squared. And then we have r d theta. And then those are the integration limit. So just to try to explain how do we come up with the integration formula and the integration limit. So here we are. So here, x squared plus y squared plus a squared equal to a squared, that's our surface. From the equation of the surface, we can represent the z value. But in this original equation for the sphere, z could be positive or negative. So as we're representing the positive roots, you only identify the top surface, which is why we have to double. If you integrate the z value, its area below the top surface is only half of the volume. To double that. And then we already knew the integration limit, so that's a squared minus those two, and it's going to be a squared minus r squared. And since we have the RDR, with a change of variable, a squared minus r squared equal to u, so du equal to negative 2rdr. So then the rdr and those are 2r will be the du. Then you have to put a negative there, so it's negative u to the 1/2 power is the integration function. The antiderivative using the power rule is negative 3/2 u to the 3/2 power with the power rule. That's our antiderivative. And then we can put in the integration limit. Those are the final answer. So then the volume for the sphere is 4/3 pi r squared or 4/3 pi a squared in this question. So this is a calculus version of the proof that volume of sphere equal to 4 thirds of pi r cubed. That's the volume. Any questions? All right. This is definitely a meaningful formula to remember. Copy this. And another way to remember this is volume equal to 4/3 r cubed. And number one, this volume is three-dimensional measure. This definitely power 3. The reason that it's power 3. Another thing is you can think of the derivative of this function will be 4 pi r squared. If you find the derivative of this volume formula, 4 pi r squared, that's the surface area formula. So whenever we differentiate a three-dimensional measure, we will end up having a two-dimensional measure. And then at least that's how I remember it. So derivative of the r cubed is 3r squared, and the 3 cancel that 3. That's how surface area. Also, if you cover the 4, the pi r squared is the area for a flat circle. And this is the surface of the ball is a three-dimensional surface. So hopefully, at least that made it a little bit more meaningful to think about why do we have a 4 in here. It's related to surface area itself. Surface area is certainly a lot bigger than the single flat circle. This is the area for circle, a two-dimensional circle. And another thing is there's 3, coefficient 3 in the denominator, often related to some condense of the volume. For example, a cube. Okay, a cone have a volume that equal to 1/3 pi r squared times the height. So I often think about this 1/3 is related to that 1/3. Of course, the h there is in relation to if you dissect the entire sphere, the volume of it into multiple cones. The height of every cone will be the radius. That's example. I realize it's already over time, almost time for the class to be over. We won't be able to cover any more example. That will be it for today. I haven't finished all of the grading. That's why I didn't come back with the test result, but I think we're doing okay so far. Okay. So maybe tomorrow we'll get back before the test. That's it for today. Thank you.